do we collect gases? So the last thing we need to talk about in this chapter, we're doing okay here time-wise. Last thing we need to talk about in this chapter is how to collect gases. And gases are collected via the water displacement method. So when we create a gas, we got to be able to bottle it up. And collecting a gas via the water displacement method has one fundamental problem. So this is essentially the water displacement method. And this actually, the next kind of problem we're going to work here is how they got the molecular weight of almost all the metals, even 200 years ago. What they're doing in this problem, they're dissolving a metal zinc in some hydrochloric acid. The zinc is doing a single replacement reaction, kicking out the hydrogen, creating hydrogen gas, and creating zinc chloride, which is soluble, so it just stays dissolved. So the zinc is dissolving, generating hydrogen gas, and and now we need to collect that hydrogen gas. And whoever made this image, okay, was a fantastic scientific illustrator. They did a great job. They really knew what they were talking about. So if you look in the tube, this is all pure hydrogen gas. So hydrogen gas bubbling out of here, coming off. We got pure hydrogen gas, but now we got to collect it. So how do we collect it? We're going to collect it with a filled inverted container. So if you imagine this container was completely filled at the beginning with water, and you're going to put this like tube underneath here. You're going to start generating the hydrogen gas. The hydrogen gas is going to bubble to the top, bubble, 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 and it's going to displace water out the bottom of the container. So this method is called the water displacement method, or the downward displacement of water. So you're pushing water out of the container. And here's the one fundamental flaw. This works great. This is a wonderful way to collect a gas. But the one fundamental flaw is that as soon as you create a pocket up here, a head space for your gas, you also create a region for the water to evaporate. And notice that the scientific illustrator really knew what they were talking about, because they put water molecules up here, steam, water vapor, up in that headspace, up in that pocket. So what happens is collecting a gas via water displacement, and you're going to see this in the lab on Thursday, the virtual lab on Thursday. Collecting a gas via water displacement is a great way to collect a gas, but it has one fundamental flaw. It's easy, but your gas is now going to be contaminated with water vapor. Okay, and for most applications, that doesn't really matter. Like, who cares if the gas is contaminated with a little water vapor? You just need to be aware of that. So if your gas needed to be completely dry, this is not how you would want to collect that gas. It's also going to create a problem when we go to do some stoichiometry, because the total pressure up in here is a mixture of the gas I generated, in this case hydrogen, and the water vapor. And we're going to have to account for that. Now, we can account for that using Dalton's law of partial pressure. So the total pressure, if I was to write it for this reaction, the total pressure, P total, up in that headspace is going to be equal to the pressure of the hydrogen gas plus the pressure of water, that the water vapor that is up in that headspace there. So we can use Dalton's law of partial pressure if we know the total pressure in the container, and if we know the vapor pressure of the water, we could solve for the pressure of the gas we generated. Okay, now how do we get the pressure of the water? Well, we use these charts, okay, and you'll need to use this in the lab on Thursday, which I have this chart directly in the lab. Okay, this is a table of the vapor pressure of water at various temperatures. And what you'll notice is as the temperature increases, the vapor pressure of water also increases. Well, this should make sense. At hotter temperatures, water evaporates more. So there's going to be a greater amount of water. It's going to be a greater pressure, right? So these are the vapor pressures of water in Celsius. So if we were at 20 degrees Celsius, the vapor pressure of water would be about 17.5 millimeters of mercury, right? If we're at STP, 25 degrees Celsius, vapor pressure of water would be 23.8 millimeters of mercury. So when you collect a gas via water displacement, you have to remember that your gas is contaminated with some water vapor, and we need to subtract the partial pressure of water, okay, at that temperature to get the pressure of the gas you were trying to generate. So I want to work one of these problems, okay? This is a molecular weight of a unknown metal or of a metal. This is the molecular weight of a metal by dissolving that metal in an acid and generating hydrogen gas, collecting that hydrogen gas, measuring a couple things, measuring the volume of the gas we collected, the total pressure in the system, measuring the temperature. If we know these things, if we know the mass of the metal that was reacted, we can get the molecular weight of this metal. So if you give me a second, I'm going to copy this information on the board and I'm going to walk you through one of these problems. And this should be the last new material for the gases. So essentially what we did is same thing from the other slide, right? Okay, you got hydrochloric acid. We drop a piece of zinc in here. This is stoppered. Okay, it generates some hydrogen gas. The hydrogen gas bubbles up and it displaces some water out, and we collect hydrogen gas and water vapor up in here. So the first problem, the first part of this problem is it wants the pressure from just the hydrogen. We have the total pressure. The total pressure is 1.10 atmospheres, but we want to get the pressure of just the hydrogen. Well, how do we do that? The total pressure is equal to the pressure of the hydrogen plus the pressure of the water vapor. So I'm going to subtract the pressure of the water vapor. The pressure of the hydrogen is equal to the total pressure minus the pressure of the water vapor. Pressure of the hydrogen is equal to the total pressure minus the pressure of the water vapor. So we need to go back and get the pressure of the water vapor at 25 degrees Celsius. So we need to look it up in that chart. If we go back to the chart, at 25 degrees Celsius, the vapor pressure of water is 23.8 millimeters of mercury. So the pressure of water is 23.8 millimeters of mercury. And now we have a problem. We have a problem because these units aren't matching, right? So my pressure of the hydrogen, I have the total pressure in atmospheres, but I have the pressure of the water vapor in millimeters of mercury. And obviously, I can't take an ATM minus a millimeter of mercury. So what would I advise you to do? Well, I would convert the millimeters of mercury here into ATM. We're going to need to be an ATM to use the ideal gas law here in the next step anyway. So before we can do that, we need to do a conversion. So 23.8 millimeters of mercury for that vapor pressure of water. We're going to divide by 760 millimeters of mercury. So 23.8, oops, divided by 760, that's 0.0313 atmospheres. So minus 0.0313 atmospheres. The total pressure is 1.10. The pressure from the water vapor is 0.0313. So when we subtract the pressure from just the hydrogen, that's 1.07 atmospheres. Now, in the next step, we want moles of the hydrogen. So we need to use the partial pressure of just the hydrogen. We don't want to use the total pressure. If we use the total pressure, we'll get the total moles, right? Which is the hydrogen and the water vapor. We're only interested in the hydrogen. So we need to use the 1.07 atmospheres of hydrogen partial pressure. That's what we're going to use here in the next step. So we want the moles of hydrogen. We're going to use the ideal gas law, PV equals nRT. And in order to get the moles of hydrogen, that's why we need the pressure of just the hydrogen. Okay, so I'm going to rearrange this. I'm going to divide both sides by RT. The moles are equal to PV over RT. We're going to use the pressure of just the hydrogen, 1.07 atmospheres. We're going to use the volume collected, 1.35 liters. Go ahead and get rid of that a while. We're going to divide by R, the universal gas constant, 0.08206 atmospheres times liters over moles times Kelvin. We're going to pop the temperature in there. We're at 298 Kelvin. Notice atmosphere is gone, liters gone, Kelvin gone. We're left with moles. So 1.07 times 1.35 divided by 0.08206 divided by 298. That would be 0.0591 moles of hydrogen gas, 0.0591 moles of hydrogen gas. I'm going to stop here and pause, and we'll talk about kind of how we got here. First thing we had to do is I could not use the ideal gas law right away to get the moles of the hydrogen gas. Why could I not use the ideal gas law right away? I needed the pressure of just the hydrogen. I had the total pressure of the system. So we had to subtract the vapor pressure of water out of that to get the partial pressure of just the hydrogen gas. Once we got the partial pressure of just the hydrogen gas, then we could ideal gas law it. Okay, and it was actually pretty easy. But now, what we just got is we just got the moles of hydrogen. It's 0.0591 moles. My goal here is to be able to get an experimental molar mass for zinc. So I need moles of zinc. So we now need to, in part C, convert the moles of the hydrogen gas generated, turn that into moles of zinc. Well, that's easy. That's just a mole to mole ratio, and that's particularly easy in this problem because it's a 1-to-1 ratio, right? 1 mole of hydrogen on the bottom, 1 mole of zinc on the top, and the moles of hydrogen produced is the same as the moles of zinc that was consumed. And we can get it that way. So that's my moles of zinc that were consumed in this reaction. And now it wants a molar mass. Well, earlier tonight, we just talked about how you get, or what the molar mass is. The molar mass is, and if you even just remember the units, molar mass is units of grams per mole. What is it? It's a mass in grams divided by moles. You just got the moles, 0.0591 moles of zinc. You got the denominator in the molecular weight. The only other thing we need is the mass of the zinc. Now, it says that there is a known mass of zinc. So if you read the problem, a known mass of zinc. What was the mass of the zinc? If it was a 3.50 gram mass of zinc, what would be that molar mass? So now we can calculate that. 3.50 grams of zinc divided by 0.0591 moles of zinc that must have been in that sample. And what we'll get here is an experimental molar mass for the zinc. And that comes out to 59.2 grams per mole. Now, in the real world, if I was, and I used to do this exact lab in Chem 101, we would dissolve a piece of zinc or magnesium. It might have been magnesium. I think we did magnesium. We dissolve a piece of magnesium in some 3 molar hydrochloric acid, and we would collect the hydrogen gas that came off of it. and then we could work backwards and get the molar mass. And of course, if you got the molar mass, we know the true molar mass from the periodic table, so you could get a percent error. So the last thing, and again, I don't do this lab anymore. I do the universal gas constant lab. But the last thing we could do is actually calculate a percent error. So percent error is the absolute value of the true minus the observed or experimental divided by the true times 100. So the true molar mass of zinc, if you look, 65.38. So the percent error would be the absolute value of 65.38 minus what this individual got, 59.2, divided by 65.38 again, and then times 100. So you can see how this is a pretty nice lab. You could get an experimental molecular weight compared to the molecular weight from the periodic table and turn that right into a percent error. And this person didn't do a great job. They got a 9.45% error. That's not great, right? You're usually shooting for less than 5, especially with the gas laws. Gas laws, they work, right? Gas laws, there's a reason chemistry got started by people studying gases, and that's because it's easy and you get really good results and it's effective and it works really well. So awesome.